So, dear guests, dear colleagues, welcome back to Yerevan Mathematical Colloquium. Today we have a guest speaker, Mkrtchyan, my friend and colleague and collaborator. Karapet has defended his PhD at the Physics Institute in Yerevan and is generally working with field theory, higher spin algebras, Lagrangian formulations of field theory, and has to do a lot with Lie group theory, especially. Then the rest of his academic career he has spent at different renowned scientific centers and has an extensive research publication record. He's well known among his colleagues in the subjects. So today, Karapet will tell us about something of which the title we can't see anymore. But basically, the idea is to try to present to an audience of mathematicians, a general audience of mathematicians, the kind of problems and mathematical concepts that arise in this branch of theoretical physics, so as to, on the one hand, ignite some interest from mathematicians, and on the other hand, and consequently, perhaps also give rise to some possible scientific interactions. So the format is roughly 1 hour. I'll leave it to Karapet to decide whether he wants to be interrupted during the talk or he wants to make pauses at some points so that people can ask questions. Other than that, please, Karapet, you have the stage now.
Thank you, Zirai. So please interrupt me anytime. Actually, I have some idea what I'm going to talk about, but I might end up talking about other things. That's also okay, because it depends on the kind of questions of the audience. And I have to apologize to those who are familiar with the subject, because I will try to be introductory, and I hope that the questions will lead me to the directions where it's not clear to the audience some parts, and I can give more details. So the talk will be mostly on electromagnetic duality. And I apologize for this handwriting, which is not so clear, but I will try to do my best. So I will first explain the context where this notion of duality arises. So the context is field theory, and field theory in the classical field theory, also in the quantum field theory, there are like each of them have their reincarnations of electromagnetic duality that have different nuances. I will mostly talk about the classical field theory, and the electromagnetic duality appears in the simplest example of field theory. That is also historically, I would say, first, which is the electromagnetic field theory given by Maxwell Equations. So as a teaser, I will just write the Maxwell Equations. So in the form that is usually given in the textbooks in high school, I guess, and university in the first years. So now we have two vectors, electric strand E. It's a three-dimensional vector, so we are in 3+1 dimensional space-time. So 3 space and 1 time directions. And then the vector E corresponds to electric strand and P magnetic strand. And these are fields in the sense that they depend on the space-time point. So they change during, they change in time and also across the space. So then the corresponding field equations are given by Maxwell equations that I'm writing. And the standard equations that we learn is of this form. So we note that there is some part of this equation which contains electric current and charge density, which would be analogous for the equations of second set of equations. The analogous notions would be to add something like magnetic currents and magnetic charge density. We don't usually do for 2 reasons. One is that we don't have experimentally seen electric and magnetic charges in nature, and the second reason I will explain below. It's somehow harder to introduce this notion in the setup where we have a Lagrangian formulation of electromagnetic field as a gauge theory. So first, I would like to note that if we try to put together electric and magnetic fields, they form an electromagnetic field strand. It's a two-form. I have to need some feedback from the audience, depending on like whether you are familiar with the form notations, external calculus or not. So one can define a 4x4 matrix, let's say. Which is antisymmetric and correspondingly has 6 independent components, 3 of which are electric components of electric field strand, and 3 are magnetic ones. Something of this form. Maybe somewhere I will make a sign error. So this would be the 4x4 matrix, which can be understood as having components of so mu and nu would take values from 0 to 3, so 4 possible values. When it's 1 to 3, that corresponds to space directions, and 0 is the time direction. So we would say that F0i is EI is the electric vector, and Fij is giving the magnetic vector dualized in the 3-dimensional sense using the SO3 invariant epsilon ijk. So please interrupt me whenever there is something that is not clear. Now, when we rewrite this Maxwell equations in terms of this 4-dimensional space-time quantities that manifest Lorentz invariance, and Lorentz invariance is Lorentz symmetry is SO1, 3 is the symmetry of Minkowski space. Actually, it's ISO 1,3, which contains rotations SO3 and boosts that extended to SO1,3. That makes the Lorentz group, and I stands for the translation. So there are also 4 translations in 3 space and 1 time directions. Altogether, they form the Poincare algebra. So in order to write anything that is Poincare invariant, we use Lorentz tensors that are tensors of SO1,3. Now, in this sense, the F mu is a Lorentz tensor, and correspondingly, we can write equations for it, so, which would be so this is electric current, which is combining rho e and Je, so charge density and the 3-dimensional current into 4-dimensional current. And another equation would be full antisymmetrization of 3 indices, where one is derivative on f, is equal to magnetic current in this sense. So this in the standard textbook, this is just 0 because there are no magnetic charges and currents. So then this equation can be naturally solved by Poincare lemma. So antisymmetrized derivative of the antisymmetric tensor is equal to 0 implies that this tensor itself is a derivative of something. So this would imply that where now A mu is a Lorentz vector, which would be our fundamental variable describing electromagnetic field. So for physicists, this is just elementary stuff. Everything is known. A mu is the vector potential of electromagnetic field. And what we actually end up describing is that so as long as we have no magnetic degrees of freedom, everything is boils down. So the second set of equations, Maxwell equations, are automatically satisfied for this field. And correspondingly, the only real equation is the first set, which can be derived as a variational equation from a Lagrangian. So F mu is actually this expression now. So if we variate this Lagrangian, we get the equation 1. Now, this basically gives us a setup which is completely fine for any physical configurations where we don't have any magnetic degrees of freedom. So this is basically more or less all we need to describe field theory for electromagnetic fields with electric charges. What I want to emphasize is that there is an interesting correlation that so when we want to describe certain types of degrees of freedom in a Poincare invariant manner, we basically have to put into identification, which physicists most of the time do without actually explaining the details, because this is kind of already natural map in our minds that if you want to describe particle with spin 1, then you have to use a vector field. This is can be understood in the way that the quantization of the theory of a vector field given in this form, which is the electromagnetic field, would lead to describing particles that carry spin 1. And the reason is somewhat hidden, in a sense that the actual reason behind is that if we if we start classifying particles, that are representations of Poincare algebra, we want to do classification of Poincare representations that are massless, which means that this part, so I stands for translations. So we have translations are Lorentz vectors and they commute for Poincare. And since they are Lorentz vectors, they also satisfy. So mu is the generators of Lorentz algebra. They are antisymmetric. So basically, so this is just antisymmetrization of pairs, mu nu and lambda rho, and eta is the Minkowski metric. And correspondingly, translations are vector of Lorentz, therefore they transform as Lorentz vector. Now, when we try to study representation theory here, that is classifying possible particles that live on Minkowski spacetime, what we do is that we take the two Casimirs. So one is p squared. So this is one of the Casimirs, the quadratic Casimir of Poincare algebra, and this we identify the eigenvalue of this Casimir with mass when trying to derive irreducible representations. And then there is the C4, which is depends on conventions, the coefficient, but yeah, it's a square of Pauli-Lubansky vector where W is something like this. So W is what is called Pauli-Lubansky vector, and its squared gives the fourth Casimir. And so these are the only two Casimirs. Actually, the second Casimir also its eigenvalues are parametrized with mass and spin. S is spin. So for massive particles, we have a clear identification. So m squared is not zero. Correspondingly, the fourth Casimir defines the spin. In the massless case, things are a bit more tricky because there is no spin, but there is helicity in 4D. But effectively, it's very similar. And what this says is that we basically need to start from what is called the little group, take the part of Lorentz that commutes with the given momentum. And this is usually, for massive case, would be SO3. For massless case, this would be ISO2. So again, if we are interested in the massive case, we can take the finite dimensional representation, and this would parameterize spin. If in the massless case, we are interested in those massless cases where we have finitely many degrees of freedom, so we take the translation part to act trivially. Correspondingly, we have SO2 representations. And furthermore, we can try to make identification. So take the massive case and take mass goes to zero, then we are led to the massless case. And these are in one-to-one correspondence with the field equations one can write, quantization of which will give rise to these particles. So then this actually says that if you take a representation for this SO2, that is carries one label. So we give a label for this SO2. This lambda label would correspond to helicity. And in case of SO3, we take different spin representations. And what we do is the following. We take any SO3 representation can be parameterized by a symmetric tensor. So we take the symmetric tensor of rank S, and that would be symmetric tensor of SO3. Then we put in equivalence, and one can show that there is actually this equivalence with a symmetric tensor of Lorentz that would satisfy certain equations. So it satisfies what is called Klein-Gordon equation, which is D'Alembertian plus mass squared on this tensor is 0. Then it's also divergenceless and traceless. This set of equations make sure that we are describing a representation that is labeled by a little group index of this spin. So there is one-to-one correspondence between the representation that is actually given by the labels of the little group and the representation of the Lorentz that we use to describe the field theory. This one-to-one correspondence is somehow in the minds of physicists. They never question this. They never question. So when you say that I am going to describe a particle of spin S, a massless particle of spin S, they already know that you are going to take a single tensor of rank S, symmetric tensor of rank S of the Lorentz algebra, and then write corresponding standard actions for it, and do some things with it. So that means that.
May I ask, if I may interrupt, may I ask, so helicity is some kind of property of spin? So these are spin, mass, helicity, all these things that describe.
So you can see that mass is here in the equation. So it is some property, but helicity is a bit more tricky, because so what happens is that if we are discussing the 4D, this is the simplest case. One can actually physically imagine that you have a particle with a given spin, and when you have a mass, so your spin is a vector that has that is different from the momentum vector of this particle, and there is a kind of different potential projections of spin to the vector of momentum. And this actually can be for massive case. I mean, this is we are now, I mean, in the language of particles. It's a quantized concept. So you basically can see that the spin can have several possible projections, not infinitely many possibilities, because of quantum properties. So we are taking some finite dimensional representation of SO3, which has several states. So when the spin is S, it's the label of SO3 representation. Then you have these projections can be like, it's a finite dimensional representation. So it goes from S to minus S, jumping by 1. So it's 2S plus 1 possibilities. So for massive case, when you do the massless case, somehow physically one can imagine that it's just because massless particles move with the speed of light, and that their spin has to be somehow projected to the momentum in two only possible ways. Either it's parallel or anti-parallel, and so the helicity will be corresponding. So if you have a particle of mass, non-zero mass and spin S, then you somehow go to a regime when the mass goes to 0. Then the spin of this particle can have only two projections, which means that this is what we call helicity. So it's either plus S or minus S. You don't have middle options. And so in this sense, the representation of SO2 takes a label that is just a single label, and this is the helicity. So this can be plus S or minus S. These are different representations, separate representations, but in in field theory, they always come together. For example, when I wrote this Lagrangian for electromagnetic field, so when we study what is the corresponding particles that it describes, these particles have only helicities plus minus 1. I mean, now we can see that, so this theory describes helicities both plus and minus, so that you cannot just take one of them and describe separately. This is asking different people, they will give different reasons why this should be so. One standard argument would be probably CPT theorem, which says that if you change simultaneously the space and time directions and also conjugate charge, so change also sign of charge of any particle in your theory, then you get the same theory somehow. In this sense, this change of space and time directions to their opposite, parity transformations, would change also the two helicities. So they have to come in pairs, so that this is invariant. This is one way to see probably, but at least in the standard examples, we describe pairs of helicities always in 4 dimensions. And in fact, there's only one representation that has single degree of freedom, not 2, massless representation, which is the trivial one. So that corresponds to scalar field that has 0 spin. In this case, we have only one copy, not 2. I don't know if I answered the question.
I learned something.
Okay. So the notion of spin is somehow intrinsic degrees of freedom of given particle, and this is has to be parameterized by taking a certain non-trivial representation of the massive little group, and in the same way the helicity. So we are now discussing 4 dimensions. Here it's kind of the irreducible representation of ISO2 is 1-dimensional, so there is only single helicity. It is just in every field theory, they come in pairs whenever the representation is non-trivial. So this is just to keep in mind. And it is very important to describe. It is very important to describe our field theory with the maximum number of symmetries we have. So in this case, we are interested in relativistic field theory, so we want to have Poincare symmetry built in our description. That's why we do this effort to write everything in terms of Lorentz tensors. This is important for several reasons. One is that this is the symmetry that constrains strongly possible interactions in your theory. Otherwise, it is very hard to, I mean, you know that the symmetry is there. You want to write interactions as arbitrary as you can, but respecting this symmetry. The most natural way is to use Lorentz tensors. So that motivates us to describe our field theories in terms of Lorentz tensors. But then for the massless fields, this naturally comes with a price, because the number of degrees of freedom we want to describe is small, but the Lorentz tensors carry, I mean, more components, and there has to be some way to get rid of them. Also, just using the trivial representations wouldn't work in this case. So what we do is that I did all of this introduction to mention how do we use Lorentz tensors to describe massless degrees of freedom, and the standard thing is to mention that this right. So this example will be spin 1 as much as I can. Whenever some generalizations are needed to give the general picture, I will mention also, as I did for general spin and helicity, but we are going to mostly talk about spin 1. And spin 1 is the electromagnetic field. Now we can see that this description, if we forget for a moment about the matter interactions, so extra sources, just the electromagnetic field itself, it has a symmetry that is, we can see that we have, if we change our field A mu by an arbitrary gradient of a scalar, F mu will not change, and correspondingly the Lagrangian will not change. So our theory is inert to these local transformations. And this is what we call gauge symmetry. Many of you are familiar, I'm sure. So when we are trying to describe massless degrees of freedom in terms of Lorentz tensors, it is always necessary, whenever the mass is, whenever the spin or helicity is 1 or higher, we necessarily need to use gauge symmetry to describe this degrees of freedom. So A mu generically has 4 components, but we know that we are describing 2 helicity modes, plus minus 1. So we are basically using a redundant description. Therefore, there is some symmetry that identifies different field configurations, which is this gauge symmetry. Now, this is already somehow using more fields that we need to describe our system, because we pay this price to have manifest symmetry. Now, what is interesting is I started from the very beginning writing this ugly Maxwell equations because I prefer them in a Lorentz covariant way. They are much simpler to my mind. So, but the way they are written in this form, we can actually notice a symmetry when we don't have any charges. So we take out all the matter, all the currents, all the right-hand sides that are encircled in red. Then these equations can be understood in a very simple way. So if we write in the form notations, I'm not sure if it's familiar to everyone. So basically, I will write, but then explain what is what. This is the equation that we write in this simple form, but what is meant is this equation. So fully antisymmetrized derivative of f, and then star f is now here we have a metric that rises and lowers indices, as I wrote here. The metric is Minkowski. So, and we have another Lorentz invariant tensor, which is the fully antisymmetric with 4 indices tensor, because we are in 4 dimensions. Now, the 2 equations without sources take the form where they say that, so this is called Hodge dual, to those who don't know. So the equations say that both f and its Hodge dual are closed. So they satisfy the antisymmetrized derivative equals 0 equation. And naively, one way to solve it is to take one of them and solve by saying that the f equals 0 by Poincaré lemma implies that f is equal to dA. This is what we do usually. In principle, one could do the opposite. One could say that the star f equal to 0 implies star f equals to dB. Or actually, one could do both. So in case if we do both, what we forget here is that f and star f are Hodge dual of each other. So in order to reinstate that, so that we have the right equations, this would imply that dA equals to, well, star dA equals to dB. This is a first order equation, and we are using 2 gauge potentials instead of 1. And this has an extra symmetry that is already visible in the Maxwell equations. that was basically the reason why I wrote them here, and I failed to show the reason all the time. So we can see that we can take transformation of electric and magnetic vectors, basically rotating them in by an angle alpha. So a rotation in a plane that has nothing to do with the space planes where they take Fourier's vectors. So this is an extra symmetry of this system whenever there are no charges. And whenever we introduce charges of only one type, this symmetry is broken. And if you want to reinstate it, we have to introduce also magnetic charges and also make a transformation that also rotates charges. So this symmetry is the subject of the talk today, which I was leading to. So this is electric-magnetic duality symmetry. This is a continuous duality symmetry, which is parameterized by, it is the group of this symmetry is SO2. We could so we could have a discrete subset of this symmetry, which is also referred to as electric-magnetic duality symmetry, which is actually Z4, which basically says E goes to B and B goes to, let's say, so this is Z4 symmetry, which is also often referred as electric-magnetic duality symmetry. But what we are interested in is the continuous duality symmetry SO2, which is a very strong statement in a sense. And in fact, as I said, so the Maxwell equations, we were able to rewrite them using Lorentz tensors. So in order to manifest this symmetry, we had to extend our setup. We had to introduce more fields that we actually have degrees of freedom in our theory. What happens here is that there is some clash between this symmetry and the Lorentz symmetry. So when we try to manifest Lorentz symmetry, as we can see by introducing this Lagrangian description using the vector A, this introduces some sort of non-equivalent description, because I mean, not a democratic, let's say, description where one of these equations we solve and the other we don't. Instead, when we do solve both of the equations, then this I would call democratic formulation. And here we can see that we can actually introduce the full SO2 symmetry at the level of fundamental variables that enter the equation. So we can actually say that there's as vectors, as Lorentz vectors, they can transform exactly same way. Now this should not be, this P should not be confused with the 3-vector P of magnetic, which has the arrow on it. I hope that's not confusing. So what we see is that we have a description of electromagnetic fields without charges that is given by first-order equations and manifests this electric-magnetic duality symmetry. the problem with this equation is that it's not easy to write a Lagrangian from which this equation stem using variational principle. So on the other hand, if we give up Lorentz covariance, it was shown that one can write a Lagrangian relatively simply using two vectors that are three-dimensional vectors. So we somehow break Lorentz to SO3, and we can write a field theory with the Lagrangian that gives the right equations and also manifests the SO2 symmetry. So somehow the clash of these two symmetries, Lorentz and the electromagnetic duality, is somewhat strange feature that also doesn't let us to write a simple Lagrangian that would give us democratic equations. So the all of this introduction was to explain what is the point of the work that I want to review, is to write a Lagrangian that gives as its Euler-Lagrange equations the electromagnetic field equations of the first order form that manifest electromagnetic duality. And again here, where I'm not going to refer to charges, extra fields, or any matter that is interacting through electromagnetic field, but the description of electromagnetic field itself. The reason why this democratic description is important can be somehow understood already from this way that we write the standard electromagnetic Lagrangian, which is that we need the a mu potential to couple to external sources. And if we were to have also magnetic sources, we would need also this potential P that would also we would need both A and B that would couple each to their sources. So the magnetic charges would couple to P. And it is not easy to write in the standard language magnetic coupling. The reason being that, as you can see from this equation, even though P is by itself related to A, but there is no simple local solution for P in terms of A. If we had this, if we had the easy solution relating P to A algebraically or using differentials, but in a local way, then we would just easily couple also to magnetic matter, the description that uses only A. But that is not straightforward to do. In fact, there is no local solution without violating Lorentz symmetry. That's why it is complicated to have magnetic charges, and it is somehow nature coming to rescue the standard physics, saying that, okay, there are no magnetic charges, so you don't need to do that. It is not fact that there are no magnetic charges. Actually, the current consensus seems to be quite the opposite. But at the same time, the standard approach to electromagnetic field theory remains prevalent because first, we didn't yet discover these magnetic charges. And second, it's easy. So instead, what I'm trying to say is that, so there is a formulation where one can try to basically derive equations of electromagnetic field from a Lagrangian with a full Lorentz symmetry and electric magnetic duality. For that, I will just write the equations that we want to derive. So the equations would be, let's say we have two vector potentials. There above I was writing A and B. Now let's label them as A with an extra index where B goes 1 and 2. And now what I want to derive as equation is that star DAB equals to epsilon BC TAC. So epsilon BC is antisymmetric, and it is invariant tensor of the SO2. And we can take the, so we can actually agree that, for example, epsilon 1, 2 is equal to 1. Now, this is the equation I want to derive, or if I want to write it in a more friendly way, similar to Maxwell equations, I would say I want to write equations in terms of two variables. Let's call it HP, which is a two-form. So A would be one-form field. Now I'm writing in terms of two-form. This would be the set of equations I want to actually derive. So HP is a two-form, or in other words, it's an antisymmetric tensor representation of Lorentz group. So of course, this we can solve as we did in the above, and we can say that HP is equal to T of AP. But at the moment, we don't have to do that. So I will show the solution to the problem immediately, and then we can actually discuss what are the tricky things. So as we were doing for standard description of electromagnetism, we started from the need to describe 2 degrees of freedom, which are plus minus helicities of the electromagnetic waves. So this is known from school physics as 2 polarizations of the photon. We start from that, but eventually in the standard approach, we describe it by using vector potential as our fundamental variable, which is has 4 components. Now, that's the price to pay for Lorentz symmetry. Now, when we want to also manifest electromagnetic duality, sometimes we have to give up Lorentz symmetry. This is known. But also, you may also want to have both Lorentz symmetry and electromagnetic duality, and this somehow gives us an extra conditions, and we have to introduce extra redundancy to our description. So what so our approach would require us introducing new auxiliary fields. I will mention that this is really not the first example where people managed to construct a theory in the both Lorentz and electromagnetic duality invariant way. One approach is known since mid-90s. It's called Pasti-Sarok-Kintonin. Where on top of these 2 vector fields, one introduces an auxiliary scalar. I will not review this approach. It requires writing a Lagrangian that has some non-standard form, where you have also some derivatives of this auxiliary scalar field in the denominator of your Lagrangian. So, I mean, generically, it describes the same degrees of freedom for the free theory, and there's no problem with this theory. Nevertheless, I will mention the different formulation we came up lately, and this would be more useful also for deriving interactions for such systems. Now, the approach that we are using will enforce some extra structure, so that introducing on top of 2 physical vectors that we need, and another scalar, we call it A because somehow it is in some sense related to this A of past Arrow-Quinton formulation, and two extra vectors, which are auxiliary in a sense. So the Lagrangian that we will write will have following form. So I will write explicitly the vector indices to make it a bit more clear. So the Lagrangian that we write has this form. By the way, repeated indices are assumed to be summed over. So this is a standard convention for physicists. I just want to make sure this is clear. Let's write it here. Now I will mention what is what. So I want to note that to start with, so this is our Lagrangian. I will show that this actually describes same degrees of freedom as we were talking before, but now we introduced altogether, instead of 4, as in the standard description, 17 component fields. So which means we have so 2 A's, 2 R's, each of them have 4 components as a vector. So altogether 4 vectors that are 16 components, and this scalar A that adds 1 more. So this seems a bit too inconvenient description, in the sense that we have too many redundancies. At the same time, this description has a lot of symmetries that kill these extra components that we introduced, and eventually describes the same degrees of freedom. So I will just quickly review what is the way we show that this is equivalent to the standard electromagnetic field. So basically, one can show that there are a lot of symmetries, which I may not write all, but for example, which is key, there is a symmetry which shifts arbitrarily the scalar phi, and correspondingly some other fields also get transformed. Just as a manifestation of rich symmetries of this system. And this also means that the field A is actually not carrying any degrees of freedom. Furthermore, there are gauge symmetries that are obvious. For example, so each of the vectors that we have can be transformed with respect to gradient of a scalar, because they all enter the theory in terms of their curvatures, which are invariant with respect to these transformations. I hope this is clear. Actually, I didn't mention that by t mu, I mean t x mu. And also I'm using the fact that t mu t nu minus t nu t mu equals to 0. Therefore, delta alpha f would be 0, as I'm writing here, the alpha transformations. And in the same way, I can write, let's say, beta transformations for Q, that will be 0. Therefore, these are symmetries that are obvious. There's an extra symmetry which mixes between A and R. For example, this. So let's call this U symmetry. Where it also uses the scalar field A. Now, this might be a bit too much to digest immediately, but just to say that there's a read symmetry of this system, and that makes sure that we have no extra degrees of freedom, because we have to identify all configurations that differ by these transformations. Now, the equations of motion can be recast in a form where we will see that actually we get such structures. So this is two equations, P equal 1 and 2. What is special here in this equation is that the statement that a vector is orthogonal to some two form, and it is also orthogonal to the Hodge dual of this two form, which can be understood as in rough terms. So I can say that if we take P equal 2, we can understand this as a Hodge dual of this expression. Let's call this C P mu nu. So what I'm stating is that we have two equations which are involving the Hodge duals of two forms, and both of them are orthogonal to the same vector. In case if this vector is non-zero, so n squared non-zero, this implies that your two form is 0. So this is the main key point in this derivation, where second order equations suddenly become first order. So this is I'm going very fast through it because there's not much time, but I will just state what is the key point. So in the derivation of the Euler-Lagrange equations from the Lagrangian that I wrote, we will get to a point where we can see that we have two equations. They describe two forms dual to each other in terms of Hodge duality, which, as I explained, is like changing the indices, basically saying that star CB01, for example, is equal to CB23, or something of this form. So we are using the epsilon fully antisymmetric tensor contracted with indices to the two form to describe its dual, Hodge dual. So basically it's saying that if I have a structure where my two form is orthogonal to a vector and its dual is also orthogonal to the same vector, that implies, unless n squared is 0, unless that vector is null, it implies that this two form is 0. This key trick or property allows to derive first order equations from second order Lagrangian. And furthermore, this we will have also another equation let's write it of this form. If we antisymmetrize the, I hope this is clear. So this, I refer to this as antisymmetrization. So if there are 3 indices, then correspondingly there will be 3 terms antisymmetrized. So this equation, or in the form notations, T star H minus equals to 0. This equation, together with the equation that we derived from here, can imply, so this implies that T, so we can replace this guy using this equation. So we get basically -2 times T and epsilon. So that's kind of unimportant, but let's write THC equals to 0. This means that THP equals to 0. Now what we get, these 2 equations, are what we intended originally, as I advertised here. So up to sign, of course, this sign issue is irrelevant in the sense that one can flip it by replacing one of the fields with minus itself. So this one can write just the sign flip in the Lagrangian that will induce this sign flip also. So this is irrelevant issue. So this is the equations we wanted to derive from the Lagrangian. On top of that, what we can show is that the symmetries that we have make sure that there is a gauge transformation that brings us to the form where R is 0. This auxiliary field that we introduced will be pure gauge, which means that by gauge transformation we can fix it to be 0, which basically implies that our H is just TF on shell. So this can be done only on shell. On shell gauge fixing. And then we are left with just 2 vector fields. Just a second. There is a question.
There's a question, yeah.
Sorry, yeah, I was trying to be very quick. What I was trying to say is that these combinations that I called CP mu nu, we can actually show that star of CP mu nu is equal to epsilon PC CC mu nu. This is a property of this combination. We can actually show it by just a simple algebraic manipulation. What I was trying to say is that from these 2 equations, I am able to derive these 2 equations. So saying that star of C is up to algebraic multiplication, again turning into C. So the fact that C is orthogonal to this vector n and its star, we can show by this property. Combination of H that C has to be 0, because both C itself and its complement that is orthogonal to different set of vectors, they are both orthogonal to the same vector, which means that they have to be 0. This can be rigorously proven. It's just a I'm trying to be very sketchy about this. I hope this is clear.
May I also ask something? It is about the things that you said, just no local solution exists without variating Lorentz symmetry. Seems like it was a key point for like talking about these Lagrangians and so on. Could you kind of elaborate from that moment, because it makes things interesting? Is there underlying math under it that no local solution exists?
What I had in mind is that if we want to describe the whole system using only as fundamental variables these a's, one set of one vector, which is okay. So I think that helps. So if we want to use only a, then we should be able to solve this p in terms of a. So imagine that I have a question to mathematicians. Can you give me a solution p as functions of a from this equation? This would imply that you have to invert the Hodge-Deram differential t. There is no local solution to this, right? You cannot invert the Deram differential with in a local way.
I didn't know about that. Deram differential.
So this is basically anti-symmetrized derivative of p. I mean, in principle, one can cage fix p, so one component to be zero, let's say. I mean, but then we are losing the manifest Lorentz symmetry. But even so, I don't think you can find a local solution to this.
I was just wondering, when you say I don't think you can find, is there kind of any more math kind of thing? I'm trying to find some kind of interesting math. There seems to be some kind of very interesting math beyond that claim, you know? So is it about this Deram differential and its invertibility, you say?
Yeah, I mean, of course, one can write some solution, but it will not be local. So, for example, one can write a certain distribution and then acting by a derivative that will collapse somehow to one. Right?
But why is it that one cannot write
integral of a distribution, not a distribution?
Not a distribution, but like some solution? What is like a mathematical kind of principle beyond that? Can it be phrased like in a short way, or is it just like a?
I mean, the statement is the following: you have equation dB equals to c. Now, find p in terms of c. If there is a solution that is local in terms of c, then we would have a. I mean, then it would allow me to describe all of the magnetic charges interacting with electromagnetism in a local.
I see.
So because magnetic charges will be interacting with this second vector potential p, and their interaction, I mean, by all of the standard knowledge, has to contain certain non-locality if you think in terms of interactions with A. The question whether there is a local interaction in the democratic formulation that we are describing is still open. We are working on it in the sense.
I see.
It may, I mean, the hope is that we may find a setup where there is local interaction with matter, both electric and magnetically charged. And that would be, I mean, concrete practical use for this formulation. I mean, apart from being symmetric, apart from also giving a more interesting setup where you can easily describe nonlinear electrodynamics, which I didn't have time to talk about. I'm afraid my time is up. So the whole practical usefulness of this new formulation so far is that we managed to describe also arbitrary nonlinear electrodynamics in this setup.
Mm-hmm.
On top of that, in the nonlinear electrodynamics, there is a subclass. So all possible nonlinear electrodynamics in 4 dimensions that do not contain higher than 2 derivatives on the fields and so on, which is relevant in physics. These are described by a function of 2 variables. Now there is a specific subclass which is theories that have this electromagnetic duality symmetry. And I mean, not only the linear theories like Maxwell, which is obviously has this symmetry, but also nonlinear theories. Mm-hmm. So these kind of theories are known to exist. They are like, there's a class of such theories that is parametrized by a function of 1 variable. Mm-hmm. Now, our approach allows to write explicitly Lagrangians for these also electromagnetic duality symmetric theories. Mm-hmm. In the standard approach, using only 1 vector potential, the corresponding Lorentz invariant Lagrangian for such manifestly isotosymmetric theories is actually known to exist, but one cannot write explicitly general cases. So there are 2 examples that are well known. One is the Maxwell and the other what is called Porninfeld, and the slight generalizations of theories. So these are the only examples known that one can explicitly write the Lagrangian for such, but there is infinitely many of them parametrized by a function of 1 variable. What our approach does is allows to write Lagrangian where you have arbitrary function in your Lagrangian or for some combination of your field variables. And this is describing all possible theories that have electromagnetic duality symmetry. So this is the advantage of this formulation. But eventually, I mean, apart from this nice result, we want to eventually have another practical use of this formulation where we would be able to describe also magnetic charges interacting with the system in a certain way. And this is basically main motivation behind this study, usually in physics, because there is some reason to believe that magnetic charges can exist. Actually, one of the very early arguments in this direction is due to Dirac, almost 100 years old argument, where he claims, well, he shows that if you have also magnetic charges, then quantum theory requires that there is a quantization of charges. So basically, in the case that Dirac describes, let me just make this comment out of the scope of the talk. So imagine you have 1 electric charge and 1 magnetic charge, and then they interact. Then from the consistency condition of the quantum theory, you derive that E times G has to be some, I may make a mistake in the factor, but something that is related to the Planck constant because it's a quantum condition, and some integer number. So, of course, I mean, this does not fix separately E or G, but gives a condition. And this basically says that if you have some magnetic charge somewhere, then it would imply that the electric charge is quantized. And we know that in the nature, electric charge is quantized. So this is one argument why there should be magnetic charges, so that they would explain quantization of electric charges. Another generalization of this condition was later given by Schwinger, which says that take more general, take 2 particles. One of them has both electric charge E1 and magnetic charge G1. The other has electric charge E2, magnetic charge G2. Then what you get as a condition is that E1 G2 minus E2 G1 equals to some number.
The commutator.
Yeah, actually, commutator. In case of Dirac, you basically take that one of them does not have magnetic charge and the other doesn't have electric, so you get only one of the terms. So this is the thing. And in fact, this condition is SO2 invariant because, as I said, if we were to have a theory that has both electric and magnetic charges, Maxwell equations say that when you rotate electric and magnetic fields, you also need to rotate the charges. So what is left invariant under this rotation is this condition. So this is consistent in a sense.
All right. So since the talk has smoothly metamorphed into a discussion, then let's maybe invite further questions from the audience and formally begin the Q&A session. But basically, it has already started. Yeah, please, questions from the audience. I saw there was a follow-up question in the chat. Maybe you can have a look, and maybe the author of the question can raise it also in person, please.
Yeah, I just asked what was, you said the first type of theory is a Maxwell type of theory. I didn't catch what was the second type of theory.
I see. So what
If you can write it down.
There is actually infinitely many theories of that have electric magnetic duality symmetry. And it is known since almost 100 years, apart from Maxwell, another theory, which is the so-called Born-Infeld theory. So this theory has an interesting property. It was introduced for different reasons. The reason was that people were interested in finding nonlinear electrodynamics that would have finite energy for point charges. So in case of Maxwell electrodynamics, when we think of point charges, it turns out that because of the Coulomb potential of these point charges, if you compute its full energy, it turns out to be infinite. This was considered a problem 100 years ago, although eventually, quantum field theory seemed to have resolved it in the sense that when we study quantum field theory, this issue is irrelevant. But back in the time, people were thinking in terms of classical theory, and for them it was important to find a theory that has a finite energy for a point charge. And this was the motivation that led Born and Infeld to derive their nonlinear electrodynamics. But what turned out is that this is a very generically interesting theory that pops up in many different contexts in physics, in particular in string theory, somehow it comes out. And the reason is that it has some sort of a nice geometric structure. If you want to write a Lagrangian for it, one would say that, so the Lagrangian would be something like square root of determinant of this. So it is, one way to write it is in this form. So taking the metric, in fact, one can also take it to be not Minkowski, but any other space-time or even dynamical metric in general relativity. And then one can describe such a nonlinear electrodynamics. As you can see, this would be basically, there's always this coefficient here, which is in string theory, this pops up and this alpha prime is related to tension of the string. But generically, this would be some nonlinear theory of electrodynamics. And it turns out that this theory also has duality symmetry. So this is the another interesting example of duality symmetric theories. What I was mentioning is that in our formulation, we basically can write infinitely many duality symmetric theories that are parametrized by a function of one variable. And it can be written in a form, I can quickly write it, which is basically, the Lagrangian will be again very similar to what I wrote before. I write form notations for just simplicity. So this I wrote before what actually this means. So this would mean that it's f mu nu q lambda rho and epsilon mu nu lambda rho, just for simplicity. And now this is the free Maxwell, but we can add to it arbitrary function of a certain variable we call w, and this w can be written as square root minus determinant of h, where h I can write explicitly as 2 by 2 matrix. As you can see, it's just this combination squared in some sense, and the two indices p and t remain. Now we take determinant with respect to these two indices, and this is just giving us one variable. And the hash, as I wrote before, h is the f plus aq in terms of our variables. So then we have basically, you can give me a function of one variable, I give you a theory of manifestly duality symmetric nonlinear electrodynamics. So there is this way of thinking in this field of physics that some symmetries are hard to, some theories with the symmetries are hard to describe. That's why we have to break some of the symmetries. So we describe it in a way that is not manifestly symmetric. What we show in this example is that it's actually the opposite. When you manifest more symmetries, then it becomes possible and easier to write Lagrangians that have these symmetries. In the standard formulation, I will also comment about this. In the standard formulation, general nonlinear electrodynamics of this form is a function of two variables, where S is now we have only one f, as you remember, it's just a curvature of the A mu, and P is. So these are two invariants one can write, Lorentz invariants, and the Lagrangian is arbitrary function of these two variables. And what we actually see is that if we, let's construct also some objects that are this makes it somehow simpler to write the condition of duality symmetry. So now I write the Lagrangian in terms of these new variables u and v. The duality symmetry condition is this. Now this equation is treated in the classical book of Courant and Hilbert. It is known that there's like infinitely many solutions parameterized by a function of one variable. And when we were starting working on this nonlinear electrodynamics, we didn't know about this classical treatment, and I asked Jiraj to solve this equation. So he came up with the solution, which eventually we found in this book. So that's that's the setup. The solution, unfortunately, cannot be written in explicit functions. Therefore, that somehow is for physicists of less practical use, although for mathematicians, I mean, non-explicit solution is a solution, there's no difference. The nice advantage in our formulation is that everything is explicit. So.
Right, yes. Further questions, comments, explicit material? If we have no further questions, then yeah, let's thank our speaker and let's finish. Yeah.
Question.
Is there a question?
Well, maybe just yeah, I saw a raised hand. Maybe it was a mistake. Anyway, no.
Okay, thanks to everyone. And this is the end of the recording as well.